Okay, so you learn about electrical synapses and chemical synapses. Let's do this learning catalytics. Look with each other, close your eyes. Don't look. How many voted for electrical? Electrical. What is it doing better? Electrical. Just, you don't answer the question yet, but yes, it's faster, right? Basically, ions come in, reaching the connections, reaching the electrical synapses, boom, move to the next one, except for a very short delay. You can think about a presynaptic and postsynaptic as almost one union, right? Running, tiny delay, boom, continue. That's faster. So why chemical? I mean, wouldn't it be great if we just, boom, turn it on, the switch, and then move all the way? Isabel. It will give more variation. What do we need variation for? Okay, respond to situation. Okay, we will address that. Good answer. Anything else? Yeah. Why would it weaken? No, why would electrical weaken? Is that what you meant? Maybe I missed that. The ions will move. They will run an action potential, action potential, action potential. Once they reach the synapse, boom, they will reach the other one. Again, it's more like one long neuron. What else? I'm looking actually for a word. Let's see, Miranda. You're saying that they're more abundant in the brain, so it basically, if they're more common, probably they're better. Doesn't work for me as an excuse. Maybe they're more common. In many cases in evolution, we see a result that is not necessarily beneficial. It might be not advantageous, but it's a good clue to suggest that. But what about the mechanism? Chemical is slower, right? So why do I want slower? What can I do, Diego?
And maybe it's more specific.
It's more specific, it's more regulated. I was looking for the word regulated, but basically you guys addressed this. Electrical, once I turn the switch on, boom, it's on. Throughout the neurons, throughout the synapses, I cannot stop it. In biology, as much as it's important to produce work, to produce a process, action potential, or something else, it is just as important that we can regulate it and say, we want it, but only when we want it. Too much is just as bad as not enough. So, in some cases, especially when we talk about short interneurons in the brain, we just want to do it fast. Electrical synapses are wonderful. But in most cases, the reason why it's more abundant is because we can regulate that, and this is what we'll talk about today and continuing on Thursday. So, we compare and contrast between the electrical. Let's talk a bit about what happens first of all. Let's just make sure we got it all. You guys will help me. I know you're prepared for that. Here is the axon. Imagine that my laser point right here presents the action potential running in the presynaptic axon, a neuron, reaching it here, and here it is. Now we're zooming in, and right now we opened calcium what? What's your number one? What type of voltage-gated channels? Wonderful. Now, what are these ions that I showed here? 1, 2, 3 that came from the axon. Are these calcium ions? They're sodium ions, right? So why do we call them calcium voltage-gated channels? Because they let calcium in. Voltage-gated channels don't care what's the identity of the ions that create the voltage change. They create about charge. They need negative 55 or whatever threshold they have. They don't care whether it came from chloride, sodium, potassium, or calcium. We call them calcium voltage-gated channels because they are specific to calcium coming in. So action potential moved, open sodium voltage-gated channel, sodium voltage-gated channel, sodium voltage-gated channel. At some point at the axon terminal, they open calcium voltage-gated channels. Calcium comes in, and as a result of different processes, that for the sake of this class, we will call them together as one word called magic. Okay, magic happens, and as a result, what we have are vesicles fusing to the plasma membrane and releasing the content, which is going to be the neurotransmitter. Our electrical potential basically change into a chemical potential. Okay, sodium ions, and as a result, calcium magic release, and we have neurotransmitters. They will go into the very short but existing synaptic cleft. This is an example of acetylcholine. It doesn't have to be acetylcholine, it's just one of the neurotransmitters. And then either directly on ion channels or indirectly, but eventually opening ion channels, we will open what? Voltage or ligand-gated channels in the postsynaptic neuron? Ligand, not voltage. Because this is a dendrite or a soma or even an axon, but that area where we don't have enough voltage-gated channels. So what type of potential do we create here by allowing sodium ions to move to these ion channels? First of all, what was just the sodium? What did it create? D or hyperpolarization? D or hyper, guys? Depolarization. What is that? How do we call this change? If it's not voltage-gated channels, how do we call this? Local or graded potential, exactly. Okay? So, as a result of opening the ion channels in the postsynaptic neuron, what we created is a local change in the postsynaptic neuron. So, here we are zooming, let's say, on this area. And what we will have is, as a result, let's see if I can draw here. Okay. Okay, I will zoom in on this area and just show you, let's see, I'll put it here. Here's a membrane, and here is the axon terminal, okay? You can see my amazing graphic skills. And now I have, plus will represent sodium ions, right? And now, as a result of the calcium neurotransmitter, etc., I open sodium channels. So now what I will have sodium ions coming in. And what I created is a local change. When it comes to a neuron synapse, we give it a specific name of that change. It's a change, a local change in the postsynaptic neuron, right? We call it EPSP. Postsynaptic potential. It's the potential in the postsynaptic neuron, and specifically here we talk about excitatory. It's a graded, it's a local potential. Again, it's not an action potential. Why excitatory? Because what will these sodium ions, what this local potential will do eventually? It will help the axon hillock, the neuron, to generate an action potential. It will excite that neuron. So EPSP is just another name for a local potential. It's local potential, but specifically in the postsynaptic neuron. Now, if this local potential is strong enough, I need an answer from all of you. Can I generate an action potential right here, where I'm showing my laser point? Yes or no? No. Why not? Not enough voltage-gated channels. Wonderful. Where is the first place where I can actually generate an action potential in the postsynaptic neuron? Axon hillock. What happens to those ions, the pluses here that I put? Can they diffuse and reach the axon hillock? Yes, because local potentials can diffuse, right? So if I have enough pluses, enough sodium ions that will reach the axon hillock at the level of reaching and will change the potential at the axon hillock, when we reach a threshold, that will generate an action potential. Okay? Here is measuring the membrane potential at the axon hillock. And what we see here is a single EPSP. Single EPSP meaning we fired one presynaptic axon, this one. We open channels, of course they close at the end, right, because they have to close. Many sodium ions came in, diffused, that's what I have at the end. Did I reach a threshold? The answer is no. So a single EPSP, in most cases, will not be able to lead to a threshold and eventually an action potential. Any questions so far about EPSP and why you don't have an immediate action potential because of that? So what can we do? If I do want through that synapse to generate an action potential at the in the postsynaptic neuron, what can I do? If one EPSP is not enough, maybe we'll summate, maybe we'll sum them up. And there are two ways to summate, to add them. One that is spatial and one that is temporal. Spatial in space. I here open a channel, right? And let some sodiums in. But maybe I can just flood this cell with sodium ions by not stimulating it only here in this synapse, but through multiple synapses. Look at the blue arrows here. Maybe one here, and one here, and one here, and one here. So now at a given time, I will have more sodium ions that made it in, and I will have more sodium ions that will diffuse all the way to the axon hillock, and maybe that's exactly what I need to reach a threshold. Once I reach a threshold, I can throw the stimulus, right? It's an all or none. Turn the switch on. Questions about spatial summation of EPSPs? Yes, Malik. Just speak louder.
The location of the synapse, is it going to be like extremely important? Because I'm assuming that if the synapse occurs close to the axon, how important it is.
Wonderful. A wonderful question. Malik is asking, is the location of the synapse relevant here? Will I have a different effect if I compare a synapse here, this blue arrow, compared to a synapse here? Imagine I'm adding a blue arrow here. Will they have the same effect? What do you think, guys? They won't, right? Because here, ions will diffuse to the axon hillock. Here, maybe just a few will make it to the axon hillock. The further they are, the greater the chances that they will diffuse and leak, and I will not have an impact. Therefore, we cannot really answer a question, for example, of how many EPSPs do you need in order to generate an action potential, because it depends where the synapse is. Maybe you'll need 5 if they all came from here, but maybe you'll need 500 if they came from here, from that area. Excellent question. Anything else about spatial summation? What is temporal summation? Can anyone guess? Temporal means?
Exciting the same site over and over.
Exactly. Exciting the same site, the same synapse over and over and over. That's temporal summation. So we said EPSP cannot induce an action potential. Remember what we did is secreting a neurotransmitter that opened the channels for just a bit and the channels closed, right? Let's give numbers. Let's say that 50 sodium ions, not real numbers, but just an example. 50 sodium ions made it in that millisecond or few milliseconds where the channels were open, right? But if I'm firing a new action potential from the presynaptic neuron, I'm releasing more neurotransmitter that will open the channels again. Before those 50 that made it in already diffused everywhere. So basically what I'm doing, I'm firing in the same synapse, opening channels, opening channels, so many ions are able to get in, and I increase the number of EPSPs. Okay? So in this case, it's not about adding synapses, but it's firing faster. Am I limited, by the way, in how fast I can fire? I'm limited by what? By the absolute refractory field. Wonderful. Because I cannot fire immediately. I need to wait a tiny bit and then fire again. But I can fire, when I say fire, of course, it's generating an action potential from the presynaptic neuron, fast or faster or very fast, up to the limit of the absolute refractory period. These two summation mechanisms are not mutually exclusive. You can fire more rapidly from one synapse and add more synapses. You can fire more rapidly from some of those synapses, but not from others, etc., etc. At the end, you either make it to the threshold or not make it to the threshold. It's a binary output. Yes or no, that's it. Any questions about EPSP's summation? Yeah, I just want to emphasize this again, because I know that you know this, and I know I mentioned this. You add more synapses, you fire them more rapidly. It doesn't affect the ability of the soma and the dendrite to generate an action potential. They cannot generate an action potential in normal circumstances. You don't have the voltage gated channels. It will still happen only at the axon hillock. How are we doing this time? Okay. So before we leave for today and continue, we'll complete the synapses on Thursday and start with the brain. But before we do that, Let's go back to and zoom out. We talked about so many small details. Let's zoom out and understand the big picture. Okay? So when I introduced the action potential, it was last week, I told you that, okay, let's say we have a stimulus, and I gave an example. Let's say that I am opening a channel here next to the axon key-lock with a ligand and sodium ions coming. Okay? What really serves as the stimulus for the action potential that is generated at the axon key-lock? Okay, I want you guys to think about it and tell me what's the stimulus. It's not a ligand-gated channel that are just open next to the axon key-lock. What is the stimulus that generates it, based on what we just talked about, all the EPSPs and everything? How does it all start? If you're in a postsynaptic neuron, what allows you, what makes you, what would be the stimulus that will allow you eventually to generate an action potential? Talk with each other for a little bit. Let's make sure we got it. I'm going to turn the lights on, lights up. So here is a neuron. This is a neuron. You have to believe it here. It even has a smiling face. That's the axon key-lock. And we are either going to generate or not generate an action potential here, right? In the original example that I gave you, we started by a stimulus by opening channels here, allowing sodium to come in. That's again not exactly the case. What serves as a stimulus? Who wants to explain? Andrew. Perfect. It's a local potential that comes for the summation of the EPSPs that came from the soma, from the dendrites, maybe even from the axon close to the axon key-lock. So basically, if these are two neurons, presynaptic neurons, synapsing with a postsynaptic neuron, they will generate what? Local or action? Local or action? Local and local, right? And those local potentials will diffuse. Those local potentials, those EPSPs, will be the ones stimulating, and if they are strong enough, will reach the action potential here. Generate the action potential at the axon key-lock. Action potential will move, and reaching its target. Now this neuron that used to be a postsynaptic neuron is going to be a presynaptic neuron for the next neurons in the circuit. So the big picture eventually is this. Okay? We have action potentials if they are generated. We have a resting memory potential to begin with, and we have a graded potential upon a stimulus that is produced here. And only if it's strong enough, it will create an action potential here. The action potential is generated with axon key-lock as a result of the stimulus reaching the threshold. The stimulus get graded potentials coming from the dendrites of the cell body. I'm going to leave you with one question to think about. What happens if we hyperpolarize, not D, but hyperpolarize the postsynaptic neuron? We'll continue with that one question.